Welcome to this explainer. Let's jump right into it. Today, we're diving into a truly groundbreaking method called SkillOpt. We'll be looking at some fascinating research from a joint team across Microsoft and several leading universities. They figured out a way to train an AI's behavior and deeply optimize its performance without ever touching its underlying code or changing a single model weight.
So that brings us to the core question, right? How exactly do you teach a frozen AI new tricks? We had these incredible frontier models out in the wild. Think of systems like GPT 5.5 or Claude. But for the vast majority of us using them, their core neural weights are totally frozen. You can't just go in and rewire the brain of the AI, which means if you want them to learn highly specialized, complex procedures, well, it's incredibly difficult.
Here is our roadmap for today. First, we'll look at the AI adaptation problem. Second, introducing SkillOpt. Third, the text-based training loop. Fourth, benchmarks and results. And finally, portable, cost-effective AI.
Starting with Section 1, the AI adaptation problem. Let's look at the limits of frozen models.
Right now, developers are basically stuck between a rock and a hard place. If you want to adapt an AI to a specific task, you really only have two options. You either change the model weights through fine-tuning, which, let's be honest, is massively expensive and literally impossible for closed frontier models, or you rely on handcrafting prompts. But prompting? It's kind of a messy, brittle guessing game. It relies on ad hoc updates that don't reliably improve even when you give the system feedback. It's highly unstable. As the source material so perfectly points out, none of our current methods for writing agent skills actually possess the mathematical rigor or reproducibility of a true deep learning optimizer. Right now, we basically just rewrite a prompt and cross our fingers hoping it works better. We really need a way to bring the strict discipline of machine learning directly into the text space. Which brings us to Section 2, introducing SkillOpt, the text space optimizer. SkillOpt is such an elegant solution. Think of it as a separate optimizer model that sits completely outside of your main AI agent. It watches how the agent performs on a task, and instead of just wildly rewriting the whole prompt from scratch, it proposes strict, bounded edits. We're talking specific add, delete, or replace commands on a single natural language skill document. If you picture the optimization landscape, there's a massive difference here. Standard prompt engineering causes huge semantic jumps. It's chaotic, bouncing all over the place. But SkillOpt uses bounded skill edits. By keeping the changes incredibly tight and controlled, it allows the system to slowly, stably descend into the valley toward a vastly superior, highly adapted skill. And here is the absolute mind-bending reality of SkillOpt. The final optimized artifact, it isn't some complex matrix of a billion numbers. The trained parameter is literally just a highly refined, perfectly readable text file. Usually, it's a markdown file called something like best_skill.md, and it's almost always under 2,000 words. It's human-readable, auditable, and entirely just text. Moving to Section 3, the text space training loop. Let's see how we actually apply deep learning discipline to text. The pipeline architecture behind this might sound complex, but the flow is actually super logical. Basically, an agent tries a batch of tasks. Then, an optimizer model steps in, reflects on what went wrong and what went right, and proposes those small, bounded text edits to the document. But here's where the magic really happens. It forces those proposed edits through a strict validation gate before they are ever accepted. Let's break that down into 4 clear steps. First, roll out evidence. We just watch the agent try the tasks. Second, mini-batch reflection. This means looking at groups of successes and failures to find consistent procedural errors, rather than overreacting to one isolated mistake. Third, we apply bounded text updates using a strict edit budget. And fourth, that validation gate. This gate is absolutely ruthless. It only accepts a text edit if it strictly improves the agent's score on a held-out set of data. If the score doesn't go up, the edit gets tossed out. And this isn't just some clever metaphor. SkillOpt literally maps deep learning principles one-to-one directly onto text. The trainable parameter, that's your text document. The gradient is the edit direction based on how the agent did. And critically, the learning rate is your edit budget. Just like a neural network takes tiny steps to avoid overshooting and ruining everything, SkillOpt limits the maximum number of text edits per step so the prompt doesn't wildly mutate and break what was already working. But wait, what happens when an edit fails that strict validation gate?
Well, it goes into a rejected edit buffer. This is huge because it provides negative feedback. The optimizer actually learns from what failed. It remembers those mistakes so it won't propose them again. And it does all of this without ruining the skill document you've actually deployed. It's a perfectly safe environment to learn from failure.
All right, Section 4, Benchmarks and Results. Get ready for some staggering numerical improvements. So the big question, does applying mathematical optimization to a text prompt actually work in practice? Absolutely. When tested on GPT 5.5 in direct chat, SkillOpt lifted the average accuracy by an incredible 23.5 absolute points across 6 highly diverse, challenging benchmarks compared to using no skill at all. That is a massive leap in capability, all from tweaking a text file. To really put that in perspective, look at Spreadsheet Bench. This is a tough, multi-round coding and tool use task. Using standard prompting, the baseline model scored 41.8. With SkillOpt, performance nearly doubled, leaping all the way to 80.7. It essentially turns a mediocre, struggling assistant into an expert simply by refining its procedural instructions over time. And this isn't just a one-off win. Across 52 different combinations of models, benchmarks, and testing harnesses, ranging from giant frontier models all the way down to tiny nano models, SkillOpt was the best or tied for best on every single one. 52 out of 52. A clean sweep. It completely outclassed expertly human-crafted prompts and one-shot LLM prompts.
So you're probably wondering, what exactly is the optimizer writing into this text file? Well, it's discovering brilliant, highly specific procedural rules. For example, in embodied tasks like AlfWorld, it learned to tell the agent to keep a visited ledger so it stops wandering into the exact same room twice. In document vision tasks, it figured out a rule to bind questions to specific visual headers before attempting an answer. And amazingly, the system usually dialed in these perfect rules in just 1 to 4 accepted edits.
Let's wrap up with Section 5, Portable, Cost-Effective AI. Write once, run anywhere.
Because the resulting skill is literally just a text file, it is insanely portable, which delivers massive practical value. The research showed you can train a skill on a huge expensive model, take that plain text file, hand it to a tiny nano model, and that little model gets a massive performance boost. You can even move the skill across completely different execution environments. In one test, they took a skill trained in a Codex harness, dropped it straight into a Claude Code harness, and saw 59.7-point gain. It's basically a plug-and-play brain upgrade. And the cost to train this? For some procedural benchmarks, it cost as little as 0.6 million training tokens per point of test set gain. To put that in perspective for the AI world, that is basically dirt cheap.
But the real beauty for developers here is the zero inference time overhead. You only pay for the heavy lifting of the optimizer once, during the training phase. When you actually deploy the AI to your users, you aren't constantly hitting an expensive reasoning API over and over again to fix mistakes. You just load your single, deeply optimized bestskill.md text file alongside your standard agent, and boom, you instantly get expert-level procedural behavior.
We have seen today how SkillOpt completely revolutionizes domain adaptation without touching a single neural weight. It brings the strict mathematical discipline of deep learning directly into the text space, creating compact, readable, and highly portable AI skills. It leaves us with a fascinating thought to consider. If an AI's most complex procedural skills can be trained and perfected just like a neural network, but stored in a simple, readable text file, what bounds can your AI break next? Thank you so much for joining me for this explainer. I hope you found this as fascinating as I did.